Alrighty, so this is going to be our Trig boot camp, everything you need to know about Trig in order to really, well, feel comfortable with right angle Trig, be able to pass your assessments, etc. So the very first thing we need to talk about is, as I just said, when we're talking about this, we're talking about what's known as right angle Trig. So we're only talking about right triangles. If we were to look at this outside of a right triangle, it's going to look a little different. So when we're talking about labeling things as a hypotenuse, adjacent, and opposite, we're talking about being inside of a right triangle. So in order to do that, we do have to be able to label all three sides, and a triangle has three, as either the hypotenuse, the adjacent, or the opposite, and each side will be one of these things. So the hypotenuse is the easiest one because it never changes. The hypotenuse is always the longest side of your right triangle, and it is always located across from the 90-degree angle. So if we look at any of these diagrams, and we start at the right angle, which is always kind of the box, and draw across the triangle, that is where we're going to find our hypotenuse. It doesn't matter which one of these we're looking at, it's always going to be across from the 90-degree angle. So these are, the hypotenuse is not angle dependent, meaning it doesn't change, it is always the same exact side. However, when you're talking about the adjacent and the opposite, these are angle dependent. That means if we change the angle that we're looking at, these two sides are going to switch around. They are going to change. The first thing that's really important to note is that for both of these, the adjacent and the opposite are the two legs. So the hypotenuse is the hypotenuse. The other two we call the legs. And the legs can either be adjacent or opposite. The adjacent one is the leg that is touching your specific angles, whichever angle you're looking at. And that's because adjacent means next to, so using that definition. So if we look at these, the red angle is the angle that we're looking at. We've already found our hypotenuse, so we have to look at the leg that is touching it. The leg will connect from the 90-degree to the angle. That is going to be my adjacent side. Notice by identifying the hypotenuse earlier, I know that the hypotenuse is not my adjacent side. I've already found it, so it's the other side that touches the angle. This is always going to be your adjacent. Therefore, your opposite is the one that is not touching your angle, and you're going to find on the opposite side of the triangle. So if I look at the angle that I want to, the angle that we've been highlighting, I can draw all the way to the other side of the triangle, and that is where I'm going to locate my opposite leg. Notice that this one does not touch my specific angle. It's actually the only side of the triangle that does not touch my specific angle. We simply call it the opposite because you find it on the opposite side of the triangle. So once we can feel pretty comfortable with this, this is the biggest part, like I said. So here we have some practice. So the first thing you always want to do is locate which angle you're talking about. Oftentimes it'll be identified as theta, which is just the variable we use for an unknown angle. So now I can find my sides. I'd like to start with my hypotenuse. The other side then that is touching my angle is going to be my adjacent, meaning that the one across from it is my opposite. To do some practice with these, we often write these in ratios. That's what we're doing with trig. So now that I've located my sides and labeled them as opposite, adjacent, or hypotenuse, I can go ahead and write them in these ratios. We can do the same thing for this triangle over here. Notice the very first thing I want to do is locate my theta, and then I want to label everything based off of that. So my hypotenuse is across from my 90. The other side that is touching this is going to become my adjacent, and meaning that if I draw all the way across, I'm going to find my opposite. So once you get really comfortable with finding which side is opposite, adjacent, hypotenuse, these ratios that we've been looking at are really important when it comes to trig. These are 3 big ratios. Oh, there we go. So when we label a triangle, we can then find our big 3 trig ratios. So the first one is sine, and we represent that as sin, sine. We have cosine, which we represented as cos, and we have tangent, which we represented as tan, so tangent. Notice that inside of this, it says the sine of theta, the cosine of theta, the tangent of theta. By doing that, it's telling me which angle I need to look at inside my triangle. If I come over here to my triangle, I have a theta and an alpha. But because there's a theta inside of my trig ratios, that is telling me that I'm looking at this angle up here, the one that is also theta. Had it said sine of alpha, then I would have looked at the one down here. So you have to look for the hints in the problem to know which angle you're looking at. As I label based off of this, we get our hypotenuse, adjacent, and opposite. Now, sine, whenever we're talking about sine, we're always talking about the opposite side over the hypotenuse. When we're talking about cosine, we're just asking for the ratio of the adjacent over the hypotenuse. And when we're looking for tangent, we're just asking for the ratio of the opposite over the adjacent. In order to remember that, we have a trick or an acronym called SOHCAHTOA. SOHCAHTOA. So when we look at this, the sine is S. Here we have cosine, C, tangent, T. The OH means that it is always opposite over hypotenuse. The AH means it's always adjacent over hypotenuse. And the OA means that it's always opposite over adjacent. So these are our 6 big ratios here. Or sorry, our 3 big ratios. So as we keep looking, they also have their reciprocal. So when we talk about a reciprocal, we mean to flip the fraction. So sine, we said was opposite over hypotenuse. Well, if we flip that, we get hypotenuse over opposite. That's known as cosecant, which we represent that as CSC. Cosine goes to secant. So when we flip adjacent over hypotenuse, we get hypotenuse over adjacent, which becomes secant. And then the reciprocal of tangent, opposite over adjacent, becomes adjacent over opposite, which we get cotangent. The easiest way of trying to remember which ones go with which is I always say each partner needs a co. Co kind of means partner. So sine needs his co, so he gets cosecant. Cosine already has a co, so it needs a partner that doesn't have it. And obviously, we're typically pretty good at remembering that tangent and cotangent go together. So that's how I remember these. So the next thing that we're going to do is actually do some practice here. So if you're following along on your own, go ahead and take about 30 seconds and see if you can find the big 6 ratios here. All right, so I'm going to look here. Hopefully you had a chance to do this on your own and see across. So I found my theta because that's what it was telling me I was looking for. I'm going to label my sides as always. Sine, we said, is always opposite over hypotenuse, so that gives me 9 over 41. What I like to do is immediately find the reciprocal, so I know that cosecant is going to be 41 over 9. Cosine is always adjacent over hypotenuse, so that becomes 40 over 41. So secant must be 41 over 40. And then tangent is opposite over adjacent, so that's going to give me 9 over 40, which means cotangent is automatically 40 over 9. So understanding how to label your triangles opposite, adjacent, and hypotenuse, and knowing what ratio these represent is the big chunk. Like that is the material that you need to know in order to have a basic understanding of trig. Everything else builds off of that concept. So once we get really comfortable with actually finding the different side lengths, we can use this information to do something cool, like solve for a side length. So that's what we're looking at next, is how can we use this information to actually solve for unknown pieces. So if we zoom in and look at this triangle here, we're always going to base it around the angle that we know. So we have 41. From here, I can go ahead and label my triangle. Well, if I'm looking across, I know that my opposite side is 4, and I'm trying to solve for my adjacent side. So for this one, the hypotenuse I didn't actually need. That was kind of useless information. So now I see that I have O and A, and so I'm thinking to myself, oh, in my acronym, that's TOA, so I know that the tangent of some angle is equal to the opposite over adjacent. So I can use that information here to say the tangent of the angle I have is equal to its opposite, 4, over its adjacent, x. So now I've set up a ratio where I can actually solve for my unknown piece. In order to solve for this, we always want to get rid of the denominator first. Denominators are frustrating. They're in the way, so we have to get rid of our denominators by multiplying them up to the other side. Well, now that I've brought it up to the other side, I have to now think about how to get x by itself. Well, now it's x times the tangent of 41, so I know that in order to get rid of multiplication, I divide. This gives us x equals 4 divided by the tangent of 41. Well, I circled that because this would be the last algebraic stage. The next thing of that would actually be putting it into your calculator. As a reminder, your calculator always needs to be in degree mode. So let's go ahead and put this into our calculators. And we find out that x is equal to 4.60. So I'm going to do 2 more of these with you guys. Once again, if you're following along, I would like you to try this one for about 30 seconds on your own. See if you can go ahead and figure out how to solve this on your own time. Okay, so looking at this, once again, I'm going to orient myself. I have this 60 degrees. So noticing that the 2 sides that I have are the ones that actually go over it. So that means that I have my adjacent and my hypotenuse. Well, adjacent and hypotenuse, that's cosine. So I'm going to say that the cosine of 60 degrees is equal to the adjacent, which is x, over the hypotenuse of 11. Same thing as above, even though the x is in a different place, the very first thing I want to do is move the 11 over. It's in the denominator, so we got to move it up to the other side. Now that I'm here, I'm actually lucky. X is by itself, it's already isolated, so we're ready to throw this into our calculator. If you're putting into your calculator correctly, you should get out that x equals 5.5. It is always really good to double check that you are putting things into your calculator correctly. Let's just do one last problem. So once again, I'm looking at this triangle. I'm going to orient myself around the angle that's given. Based on this, I have my hypotenuse and my adjacent. I know that because the hypotenuse is across from the 90 degree. This is the side length that touches my angle. So this one actually happens to be cosine as well. my adjacent side over my hypotenuse. Now that I have the x in the denominator again, I need to move it up to the top. In order to get it by itself, we're going to divide by cosine. So anytime we're solving for an unknown sine length, we're always going to do the same idea. Using the angle you know, figure out which side length do you know, which one are you trying to solve for. Based on how those are labeled, it's going to tell you which one of your trig ratios you need to be using. Set up that ratio, move your denominator up to the other side, and then if you need to do that last step to solve for x, go ahead and do so. So this has been solving for a side length. The other big thing that we've talked about with trig so far is being able to solve for a missing angle. So here we've been talking about side lengths, but we also have to be able to talk about the angles. So that's the last bit we're going to talk about before we're actually done here. So here, if my triangle is already organized again, here are our big three that we've been talking about. Well, we can use what is known as inverse trig. And we use inverse trig when solving for an angle. Inverse trig switches the location of the theta, your angle, and the ratio. So if we did sine of some angle would give us a ratio. So if I put into my calculator the sine of 30 degrees, it's going to give me out 1/2, which means the ratio of the opposite over the hypotenuse always has to reduce down to 1/2. Well, here we have what's known as our inverse relationships, our inverse functions. We notate that they're inverses by this exponent of the -1. Now, this is not an exponent you put in. Your calculator should actually have a function that is set up like this. If you're using a standard TI calculator, you hit the button second, and then your trig ratio. So if I did second sine, that would actually give me inverse sine. So that's typically how we see this. What this would look like then is in order to figure this out, I would say the inverse sine of 1/2. That is what I'd actually put into my calculator. My calculator would say, hey, that's 30 degrees. So it's the same relationship, the same opposite over hypotenuse towards the angle, but we do the inverse one of the ratio in order to get the angle out. So that's using inverse trig. So let's go ahead and look at a example of this. So here, it wants us to solve for our missing angle. I'm going to do the same thing of labeling my sides. That means I have my opposite and I have my adjacent. I know still that that still means tangent. So I would say that the tangent of my angle is equal to 10 over 13. But my theta is inside my tangent now. So in order to get that out, we're going to use that inverse trig. And we're going to say the inverse tangent of 10 over 13 is equal to theta. This is now exactly what I type into my calculator. And it tells me that my angle is 37.57 degrees. I have one more of these before we move on. Same thing. We're going to look at the angle given, figure out what sides we have. So we have our opposite, we have our hypotenuse. Well, that is SOHCAHTOA. So I would say that the sine of theta is 6 over 12. But in order to get this by itself, I would say the inverse sine of the ratio, 6 over 12, is going to give me my theta. I'm going to type this into my calculator and, well, actually, we just saw this on the last slide. This would be 30 degrees because 6 over 12 reduces down to 1/2. So this is the idea of inverse trig. Whenever you're solving for an angle, once again, you're going to use inverse trig. And so that is your trig ratio to the negative first. Once again, your calculator does that for you. If you try to put it to the negative first yourself, you're just going to confuse your calculator. So make sure that you're actually finding where your calculator does that function for you. So the last bit of this kind of boot camp is to make sure you guys can do applications. That's the last thing you really need to know in order to really get an idea here. There are more things, but this is the last big part of it. So part of the application is being able to set up the correct diagram. You have to be able to read the problem and think critically about what is it telling you inside of this problem. That's why I really like this problem. Here it says, in areas that get a lot of snow, roofs must be inclined at a certain angle to meet the building code. That way, the snow will slide off the roof and not actually crush the house. In one town, the incline must be at least 20 degrees above the horizontal. A builder is making a roof with a rise of 5 feet for every 10 feet of run. Will this roof meet building code? So let's think about this. There's some really important information we need to know here. First off, if a problem is ever talking about rise, what that really means is they're talking about a vertical leg. As a reminder, vertical means up and down, which we can kind of get that from rise. But the thing is, it's talking about the leg here, aka not the hypotenuse. Rise is always a leg. Similar to over here, it talks about the run. Well, the run will always be your horizontal leg. As a reminder, horizontal is side to side. Once again, it's the leg, so it's not the hypotenuse. Rise and run are always your two legs. Therefore, a rise of 5 feet is going to be a vertical line of 5 feet. A run of 10 feet is going to be a horizontal line of 10 feet. That's not perfectly horizontal. Between those is my 90-degree angle, of course, because these are perpendicular to each other. And I'd have to go ahead and connect them to make a right triangle. Well, if I think about it, this would be the roof of my problem. So now we have it set up, but it says that the incline must be 20 degrees above the horizontal. So that's what we're looking for next is where do we put this angle? What angle are we talking about? Well, the hint's right here. It says above the horizontal. Well, this is my horizontal. It's my horizontal line. So my theta has to be the one that is right next to it. The one that connects above it to the hypotenuse. If I had been over here, it would have said something about the vertical. But because it said it was with the horizontal, it had to be the angle between the hypotenuse and the horizontal line. So that's how I knew how to put this in place. Now we could actually finish this out just by doing the tangent, because I have opposite and adjacent, of theta would be 5 over 10. So the inverse tangent of 5 over 10 would give me my theta. And when we do that, we get 26.57 degrees. Now, once again, we're doing applications. You can solve the problem, but you always make sure did you answer the question. So the question here says, will this roof meet the code? So I go back and say, okay, what is code? The incline must be at least 20 degrees. At least means that it has to be 20 or larger. And sure enough, this is. So we would actually say, yes, this one does meet code. Let's do just one more example. A person standing on level ground is 2,000 feet away from the foot of a 420-foot tall building. Whew, there's a lot of feet in there. So let's look at this. I have a building. And someone standing on the same level of it is 2,000 feet away. So this is going to be my 2,000. I lost a 0 in there. And we have our person standing here. So the building itself was 420 feet tall. The person is looking up at the top of the triangle, or the top of the building. So now we have a little triangle here. Once again, it wants to know what angle to the nearest degree. It helps the angle would it make with the horizontal. So once again, I'm looking at the horizontal line, and that is where I'm going to put my theta because it mentioned the horizontal. Well, now that I have this set up, it's almost perfectly exactly. That's really good English. It's perfectly like the one that we just did. So the tangent of theta is going to be 420 over 2,000. And so therefore the inverse of 420 over 2,000 will give us our angle. Meaning that the angle here is 11.86 degrees. So that actually isn't that high. Standing far enough away that in order to see the top of the building, they don't have to look too far up. They're not actually straining their neck too big. And so that is doing an application. It's making sure you can draw the picture and then think critically about where your angle is going to go. So that is really our trig boot camp. We talked about how to solve application problems, how to find an angle using inverse trig, and how to find a side length using your big 6. All of these come back around to being able to label your triangle as opposite, adjacent, and hypotenuse.